Okay, good morning students. In the last class, we have completed the design of the compression member. That is we have designed throughout the last classes, 2 or 3 classes that I have taken in the previous week. I have discussed about compression member, the load coming to the compression member, what are the general compression member, how to design a steel column, how to design an angle strut. Then we have discussed the most important built-up columns. What are built-up columns? What are the built-up systems that are provided? What is lacing? What is batten? How to design a column with lacing and how to design a column with batten plate. We have discussed all that. Now coming to foundation. First, consider you are in the RCC design. First, you have discussed the beam. Then you have studied the column, then we will proceed to the foundation. Here also the thing is same. We have discussed about the beam section, we have discussed about the column section, then we discussed the column. Now we will be discussing about the foundation under a steel column. Normally you can see I think you have seen that normally normal columns are supported over concrete slabs. Okay, over concrete blocks they are supported, but sometimes when the load in the column is very much high, then the bearing pressure given by the concrete as a reaction. What is a compression member? I think you know what is a compression member. If this is a member, then this is the column. One is the applied load P, and the reactions come from the bottom. As per the Newton's third law, every action has equal reaction, so that reaction should be sufficient to resist that column, to resist the load from the column. Okay, now if the load, the value of the P is higher, then the reaction coming from the bottom, the reaction coming from the bottom may not be sufficient. Okay, now also due to this kind of situation, the load may not be distributed properly. Okay, so that to cater for this situation, that is to cater for this situation, we provide a base plate under a column. That means there will be a base plate under the column in the conjunction between the column and the concrete block. Okay, so this is called column bases or the base plate. Okay, for example, if you want to see, this is I will discuss this 2 picture later, but in this picture, this is the base plate. Okay, this is the base plate. That means it is provided in between the column and the concrete block under the column, so as to properly distribute the load and to increase the bearing area, so that a bearing resistance is become higher. Okay, now what is the main problem in the design of a base plate? Because 2 values are the unknown, that is the area, that is the size of the bearing plate and the thickness of the bearing plate. So in our design, that is the design of the column bases, we will try to design the column base, that is we will try to find out the area and the thickness of the column base. I mean the size and the thickness of the column base. In general, the column bases are of 2 types. Number 1 is the slab base, number 2 is the gusset base. Okay, these are the 2 pictures I have drawn. It is a slab base, bolted slab base, and bolted gusset base. Okay, bolted slab base. Slab base mean, what is a slab base? Here normally a slab, that means a base plate only will be provided. This is a base plate. Okay, this is the column, this is the concrete block, concrete pedestal of the concrete block. Here the column is connected with the base plate with the help of bolted foundation bolt, and a cleat angle is provided for the connection. The connection is provided by the cleat angle and the foundation bolt in case of the base plate. But if we go into the gusset base, here cleat angles are provided, but what is the thing? That is a gusset plate also provided. A gusset plate. Okay, when the column is subjected to axial load, direct load, and bending axial or biaxial bending, then the gusset plate is generally used. Gusset base is generally used where a gusset plate is also provided. Where a gusset plate is also provided. The gusset plate is provided for cater for the extra load that is generated. So these are the general two types of column bases. One is the bolted slab base, another is the bolted gusset plate. Okay, various parts of these two connections are given. These are the base plate that I have told you. These are the foundation bolt, that is for the proper connection. This is the column, this is the cleat angle here. Here is also the cleat angle. Okay, this is the cleat angle also. And this is cleat angle. So these are the general columns. These are the general foundation modes. Now, for a live example, this is the column base which is provided under a steel bridge over a steel railway bridge. It is a bolted plate that you can see bolts are provided here. This is the column, this is the concrete block, and this is the base plate. Okay, the cleat angles are provided here for the connection. Okay, so this is a bolted slab base. Okay, so this is a live example of a slab base. Now coming to the second. So not only bolted, welded plates are also provided. Welded plates are also provided. But what is the basic welded plates are also provided? What is the difference of the welded plate with the normal bolted plate? There will be no bolted connection. So if there is no bolted connection in this plate, if there is no bolted connection, the plate is welded like this, the column is welded to the base plate like this. So there is no need of this cleat angle. There is no need of this cleat angle here and here also. There is no need of the requirement of this cleat angle here. So this is the bolted connection. This is the welded slab base and welded gusset plates. Okay, some of the welded base plate are also provided here. You can see from the IS 800. These are some of the welded. So this is welded. Okay, these are the welded plates provided here. Now coming to today we will be going for the design of a slab base. We will see the procedure of design of slab base, and then we will do our example. In the next class we will try to discuss about gusset base and the design of the gusset base. So first, today's class we will discuss about slab base. What is slab base and how to design the slab base. So when the columns are generally subjected to only direct loading, only direct load are applied to the column. That means this is a column, this is a column, only direct P load is applied here. In these general cases, the slab base is taken. Okay, the slab base is applied. For small amount of load, a steel plate alone is sufficient to carry the load. So for that cases, a steel plate acting as a slab base is provided. If the slab base is bolted connection, it will be provided with the cleat angle. In this picture, it is a plan of the slab base. You can see this is the cleat angle. This is the cleat angle which is connected with a foundation bolt. And this is connected to the base plate. This is the bolted slab base, and another is the welded slab base. So if there is a welded slab base, there is no need for this kind of cleat angle. So the welded portion is provided. This is the welded portion that is provided here. Okay, and this is the anchor bolt. What is the importance of anchor bolt? Coming to a small thing, anchor bolt. What is the anchor bolt? Anchor bolts are bolts that are provided for the proper connection between the concrete and the column, concrete and the base plate. Consider under the column there is this base plate is provided, then under the column, under the base plate, the concrete block is here. The concrete block is here. This is the concrete. Okay, this is the concrete. So for the proper connection of this base plate, and there is a foundation bolt or the anchor bolt is provided. This is the anchor bolt, so that the base plate and the concrete member becomes a monolith, a single unit, so as the proper distribution of the load. Okay, now and such a place is called a slab base. Okay, anchor bolts are provided. I have written also that anchor bolts are provided to connect the base plate with the concrete pedestal, so as to connect a proper connection between the concrete pedestal and the base plate. Now this is the basic theory that are associated with the normal slab base. Now we were coming to the design procedure of the slab base. What is the design procedure? I have told you in the theory, that is the what are the findings in this design, that is what is the thickness and what is the size of the foundation bolt, what is the thickness and what is the size of the base plate, that we will be finding out in today's lecture for slab base. Now what is the design procedure? Design procedure include finding out the size and the thickness of the plate. So step one, first one is assume a suitable grade of the concrete. Depending upon the grade of the concrete, the bearing strength of the concrete is determined by 0.456 FCK. Clause 34.4 IAS 456. So first we need to determine, but here it is also said if we are seeing IS 800, this is the column base. This is the column base. Okay, so here it is said that the bearing maximum pressure, the maximum bearing pressure should not exceed the bearing strength equals to 0.6 FCK. That means bearing strength, here it is said that 0.45 FCK, but we will take the bearing pressure we will take 0.45 FCK instead of 0.6 FCK. Why? Let us go to IS 456. This is IS 456, the design of this is IS 456. This is IS 456. It has been written here. This is IS 456. Okay, this is IS 456. We are discussing. Now, clause number 34.4. What is 34.4? This is the clause number 34.4. This is the clause number 34.4. What does it say? It says that for limit state method of design, the permissible bearing stress shall be 0.45 FCK. It is being specified by the IS 456. This is for FCK. What is FCK? FCK is the characteristics compressive strength of the concrete that we know from the concrete design. RCC design, we know the FCK is the characteristics strength of the concrete. That is the compressive strength after 28 days curing. So 0.45 FCK value we will take, not 0.6 FCK. Very much important in the exam. Do not fail by that. We will not take this value. We will take this value as 0.45 FCK. We will take this value as that. Okay, so this will be our first step to determine the bearing strength of the concrete, that is 0.45 FCK. Now as the bearing strength, now the slab base will be determined in the foundation. We have also determined by this formula, that is what will be the area of the total foundation, that is the total applied load by the bearing strength of the concrete. That means how much bearing strength the concrete is giving, that will be how much bearing strength the concrete will be is giving to resist the applied load. This is the area. So area of the slab base, that is the required area. That area is the required area. Okay, that area is the required area. Required area A equals to P, that is the factored applied load here. This is the P, that is the factored applied load here, and the bearing strength of the concrete that we have calculated 0.45 FCK. Now A is I have told you the required area of the base plate. Now to determine the required area, this is a normal bolted connector. In this picture it is shown that this is the area of the base plate. L and B is the area of the base plate. So we will find the value of A. So first then we have to determine the value of L and B. Now then coming to the step number 3, gradually, generally a square base plate is selected. Okay, generally a square base plate is provided. Size for the base plate can be determined by this formula. If the size is square, like this, if the side is A, so this will be the formula. L equals to B, this is L, this is B, so all will be same, that will be equal to root over of A. But in general this is not provided because the size of the column may not be square. So for that a special formula has to be applied. What is the special formula? This will be the special formula. Why? Consider if this is a column, I section column, it is provided here. Consider this is the I section column. Now this is the column and this is the, so this is the depth of the column and this is the width of the flange, that means the width of the column. So the base plate will be provided at a distance B, that is the overhang, that is the extra distance, that is the projection beyond the column face, and A is the projection beyond the column face. So two projections are there. So if we can determine these two projections, then we can also determine the size of the column. Very much you need to understand it very much clearly. If we can determine these two projection values A and B, we know the value of D, we know the value of BF. So if we know the value of B and A, we can determine the total L and total B. Very much you need to make it very much clear to yourself. Okay, so that's why we will be using this formula to calculate the value of B and A. Okay, D we know, that is the depth of the stanchion, because column in the steel structure column is called stanchion. Capital BF is the width of the flange of the stanchion, that we know. Now these two values are known to us. Now coming to B and A. Now what will be B and A? B and A will be the projection beyond the column face. B and A will be the projection beyond the column face. Now here also this B term and this A terms are two unknown. Now for that what we have to do? We have to make A equals to B. If we make these two projection equal, if we can make these two projection equal, then we can calculate the value of this A and B both. Similarly, the L total length will be that D plus this B, and this here is also B, and capital B will be equals to BF plus A, and here it is also A. So we can calculate the length and the width of the base plate from this formula. Very much important, because it is very much important. Okay, now coming to another clause in the IS code. IS 800 says that if the size of the base plate is larger than the required to limit the bearing pressure on the base support, an equal projection C of the base plate beyond the face of the column and gusset plate may be taken as the effective in transmitting the column load. What does it want to say? It wants to say, it is, if we see this picture, we can see sometimes the bearing area, if we consider the area from this, if we consider calculating the area from these cases, the bearing area may be too huge. The area may be too huge or very much longer to support the bearing pressure. For that, an equal projection will be applied at the face of the, beyond the face of the column. If this is the column, this is C here, this is C here, this is the equal projection. Here it will be C, here it is also C, here it is C, here it is also C. So for all sides, the projection value will be equals to C if the total bearing area coming is high. So we will take this formula as the C in A and B. So we will put the value of C in this formula. Okay, now next is the step 4. intensity of the pressure W from the concrete pedestal is calculated. That means how much pressure, that is the how much reaction force, intensity of the pressure W from the concrete pedestal. So how much pressure the concrete member is giving will be calculated by this formula. W, that is the bearing pressure, will be P, that is the applied load, and A1 is the area of the base plate provided. That means L and B we are calculated. Here we will use the value, here. This will be A1. So A1 will be equals to L into B, that we have calculated here. So L into B will be the value of the A1, that is the area that we have provided. So P by A1 will be the bearing pressure. The bearing pressure, here it is also specified here, that is the bearing pressure, the maximum bearing pressure should not exceed the bearing strength, that is equals to 0.45 FCK. We have determined the bearing strength here. That is the bearing strength 0.45 FCK. This is the bearing strength of us. So the value of the W, that is the W should be always less than, should not exceed. It is said that the bearing pressure should not exceed the bearing strength of the concrete. That means W should always be less than 0.45 FCK. This value we have to check here. This is the first check we have to provide. Now, so the size of the base plate has been determined. Now coming to the area of the base plate, that is the thickness of the base plate, that is the another unknown term. As per the IS code clause number 7.4.3.1, as clause 7.4.3.1. This is the code. The minimum thickness TS of a rectangular slab base supporting column under axial compression load will be equals to that value. Okay, they will be equals to that value. It should be always greater than the TA. Clause 7.4.3, it is been specified here also. So TS will be equals to this value, where W is the bearing pressure that we have calculated, A square minus 0.3 B square into gamma M0 by Fy, where A and B are the projection, that is the value we have calculated. This is A, this is B, the value we have calculated is the projection. It will be always greater than the thickness of the flange. Okay, this is the thickness of the flange. It will be always greater than the thickness of the minimum thickness that will be taken will always be greater than the thickness of the flange. Now sometimes that I have also discussed that if A and B, this type of area is provided, the effective area is provided. So for effective area, the C value will have to take, that is the equal projection in the all side of the column. So if the equal projection is provided, so here the A square minus 0.3 B square, this value will be changed by C square. Okay, it is written here, when only the effective area of the base plate is used, C square may be used in the above equation as in this formula. So A square minus 0.3 B square will be changed by C square. This is the formula. This is the step number 5 that we have determined the thickness of the slab. So we have calculated all the things, that is the calculation of the area of the, that is the total area of the slab, that is the size and the thickness of the slab. So all the findings have been done. Now coming to the connection of the base plate. So step 6, so connection of the base plate with the concrete, that is the concrete pedestal. Generally holding down bolt. Okay, holding down bolts mean anchor bolt. Holding down bolts or anchor bolts are provided in 2 or 4 numbers and of 20 mm diameter. Generally 2 number if the direct load is applied, and 4 number if the load value is very much higher. So we will load either 2 or 4. What is anchor bolt? That I have discussed with you, that is these are the anchor bolts. This is the anchor bolts are provided. So anchor bolts 2 or 4 number will be provided as per the requirement. Now coming to another important part, the column and the base plate connection. Now if the column is connected with the base plate by bolted connection, an angle section to be provided, an angle, that is a seat angle to be provided, and if the column is connected with the base plate with the help of a welded connection, welded, no need of cleat angle is there. So now there are two cases. What are the two cases here? First case, if a proper bearing is ensured, if a proper bearing is ensured between the column and the base plate, that means a proper bearing, proper connection between the column and the base plate is achieved, then the load is directly transferred and not need to design the connection. Okay, that means if it is being specified in the map that the column and the base plate are properly connected, there is full bearing, proper bearing between the column and the base plate, then there is no need to design the connection. However, it is advisable to use two cleat angles for the connection as the center or a certain weld for the moment, if any. So in general, if the load is directly applied and there is a proper bearing, no need to design the connection, but as a safety, a normal two cleat angles of general any size and a certain, if it is a welded connection, a certain weld size has to be provided here. Now there is another case where there is not proper bond between the column, not proper bearing between the column and the base plate. So the column and the base plate are not in proper bearing. So if the perfect bearing is not ensured, there should be the column should be welded to the base plate for all forces. That means if there is not perfect bearing between the column and the base plate, then the base plate and the column should be welded or with proper design. So how to design the weld connection for that? Now the design procedure for the weld connection. First, the effective length of the weld connection has to be calculated. Now the design procedure is, first we have to calculate the actual effective length of the weld. That means how much length we can provide, in the section. Consider this is the column section, so and this is the total area of weld we can provide here. So what is the formula to calculate the effective length of the wave? Now you can remember, you can come up, that is what we have discussed in the welded structure, that is welded connection, that is what is the effective length of a fillet weld. Okay, it is a fillet weld, not a butt weld, it is a fillet weld. So for a fillet weld, the effective length is equals to L plus 2S. That means L is the length of the length, available length, and actual length available, and 2S is the end return. What is end return? What is end return? If this is the welded connection, this is the actual available length. If this is the actual length available, this is the length available, this is the length available, then this is called end return. This is called end return. Okay, so first you have to calculate the effective length of the weld. That is the actual available length plus the number of the end returns. That is the available length we have to determine. Then in the second step, we have to assume a size of the weld and determine the throat thickness. Okay, now similarly, if we can go in the welded connection, what is the size of the weld? That is what is the size of the weld? First we have to determine the size of the have to assume a size of the weld, then determine the throat thickness. Now if we go into the welded connection, if you see the weld and welding connection, the effective throat thickness for a fillet weld, the effective throat thickness of a fillet weld, okay, for a fillet weld shall not be less than 3 mm and shall generally not exceed 0.70 and 0.70. So T is the, what is T? T is the thickness of the thinner plate of the element. So 0.7 into generally S. S is the size of the weld, 0.7 into the size. So the effective throat thickness equals to 0.7 into the size of the weld. So first we have to assume the size of the weld, that means 8 mm, 6 mm, that is the general size of the weld. Okay, then we have to calculate the effective throat thickness. Then we have to determine the strength of the weld. What is the formula for the strength of the weld? That we can determine what is the formula for the strength of the weld. That is FWD, strength, design strength of the weld. That is FWD is equal to FWN by gamma m0. That means Fu by root 3 gamma m0. So Fu by root 3 gamma m0 into area. Fu by root 3 gamma m0 into area. So here now we have to determine the strength of the weld per millimeter length. Okay, per millimeter length. So if the formula is equals to LW, then LW will be equals to 1. So this value is taken as 1. So required length of the weld will be applied load, that means the load applied and the strength of the weld. So how much is the strength that we have calculated? Now for the design to be, for the design of the connection to be sufficient, that much weld length, that is the required length of the weld, should not be more than the actual length can be provided. So actual length can be provided is the maximum value. But so the required length of the weld should be always less than the effective length that can be provided. This is the welded design of the welded connection. So we have seen how to design the welded connection, and now we will this is the end of the design. So this is the end of the design procedure. How to design it, we now know how to design a normal slab base of column. Now coming to the formula. What is the a math? Design a slab base for a column IS HB 350 at the rate 717.2 Newton per meter, subject to an axial factored compressive load of 1500 kilonewton for the following condition. Load transferred to the base by welded connection. The column end and the base plate are not machined for bearing. That means there is not proper bearing between the column and the base plate. So we have to design the base rests on a concrete pedestal of grade M20. Okay, and the loaded welded connection has to be provided. So the connection between the column base and the column is welded. So this procedure that we have discussed till now, it will be followed here. Okay, so first coming to step number 1. So let me pause that and again open it. So now we are seeing there is the procedure and here is the design. So first, step 1. What is the step 1? Assume a suitable grade of concrete depending upon the grade bearing strength. So what is the grade specified here? M20 is the grade specified here. So the bearing strength will be 0.45 into 20, that is 9 MPa is the bearing strength of the concrete. Now coming to step 2, area of the slab base required. So the required area of the base plate, that is equals to PU by 9, that is 1666667.67 millimeter square. This is the required area of the base plate. Now then we have to calculate the area of the, size of the, that is the L and B of the base plate. So we will assume this formula A and B. We will assume this formula A and B. So by this formula we will calculate the value of the overhang, that is the extra projection beyond the column base. So D plus 2B and BF plus 2A. I have told you that in these cases where A and B are both unknown, A and B which are both unknown, take A is equal to B. That means this projection and this projection are equal. So if A is equal to B and for IS HB BF we know 250 and capital D is equal to 350. For IS HB 350, this is the value that is taken from the IS SP6. So for that 350 by 2A into 250 by 2A, that is equals to that value. So from here A equals to 55.2, that is also equals to B similar because A and B are similar. Then we have to take as well. So taking A is equal to 60 mm. Therefore, L equals to 350 into 2 into 60. That is the formula. D plus 2 into B, that is L equals to D plus 2 into B. So long L, D is equal to 350, 350 plus 2 into 60, 470, and B equals to 250 plus 2 into 60, is equal to 370 mm. So this is the size of the total section, size of the total base plate. Now coming to the intensity of the pressure, step number 4, intensity of the pressure from concrete pedestal. W is equal to P by A1, so P load we know, and A1 is equal to 470 into 370, the value you have got 470 into 370, so 8.62, which is less than the 9.9 Newton, that is the bearing strength. Here it is said that this bearing pressure should not exceed the bearing strength of the concrete. That means W should be less than 0.45 SK. So it is less than 0.7, hence it is okay. Now coming to the step number 5, minimum thickness of the slab base will be calculated by this formula. Putting all the values here, A and B, we have got 15.458. It is greater than 16 mm. Now it should be always greater than TF, that is the thickness of the flange. So thickness of the flange for ISHB. Now if we open ISHB 350. Now I have opened here ISHB 61. So this is ISHB 350. Okay, this is 350. So here we have taken ISHB 350 710.2. So this is the so I think this is the value. For that, the TF, that is the thickness of the flange, is equal to 11.6. So it is greater than 11.6 mm. So hence okay, so hence provide a base plate of that much thickness and that much area. This is the required. So we have got the design of the base plate, that is the that we have completed. Now coming to the step 6. What is step 6? Now coming to similarly step 6. What is step 6? Holding down bolt or anchor bolt. Here, as the load, the holding down, only axial force is acting. Generally, two number of 20 mm diameter bolts are provided. When we will provide phone numbers, when the design is based on moment also, when the base plate is subjected to moment also, and then we will provide 4 numbers of 20 mm, because here there are only 2 numbers of 20 mm bolt will be sufficient, because only axial load is acting. So 2 numbers of 20 mm diameter anchor bolts are provided. Now coming to the step number 7, that is the design of the welded section. Now column and base plate are not properly connected, that is been specified in the map, that is the column and base plate are not properly connected. So for that we have to provide with that design procedure. So here it has been said that there is no proper connection between the column and the base plate. Proper bearing is not there. So first we have to calculate the available length, that is the effective length. So that is equals to so first available length for the around the column. What is the available length around the column? That is equals to this total length first 2, then this total length second 2, and then this length and this length and this length. So first 2 into 250, that is this 2 length, plus 2 into 350 minus 11.6 into 2. What is 11.6? That is the thickness of the flange. So if we divide, this is our 350 minus 11.6 into 2, that is this value, into 2, that means this has been calculated. So that and that is that area and that area complete, and remaining is this area and this area. So this is also 250, this is also 250. So 250 minus 10.1, that is the thickness of the wave. If we see here ISHB, the thickness of the wave is 10.1. So for 10.1 we will divide minus 10.1, then 2 into 250 minus 10.1. So this is the available length, 16.33. Now for that I have written also for ISHB 350, TW is equal to 10.1, TB is equal to 11.6. Now coming to assuming the size of the weld. So first we have to assume the size of the weld. So assuming the size of the fillet weld 8 mm, that is equals to, we have to assume that is the 8 mm size of the fillet weld, that we have assumed the 8 mm size will be taken. So now a very important thing, now welding is not possible at toes and fillet, so end return has to be subtracted for every end got effective length. So this length equals to, that I have told here also actual length plus end return, this length. But if we see in this picture, end return cannot be provided in any case. Here if it is a I section, if it is a I section like this, okay, if this is the I section like this, if it is welded, then there is no possibility of providing end returns here. So from this value, the values of the end return has to be eliminated. So we have eliminating the end return. What is the formula for the end return? 2 into S. S equals to size of the weld. So size of the weld equals to 8 mm. So 2 into S equals to 16 mm. So for each joint, end returns are provided. If this is the member, if this is the welding, end returns are provided at the joints. This is the end return, this is the end return, and this is the end return. So these are provided at the joints. So number of the joints into the end return. So number of the joints are 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8 9 10 11 12. So 12 number of joints are there. There are 2 2 2 2 and 4. So 12 number of joints. So number of the joints equals to 12 number. So total LE, that is the length can be provided, is equal to 1633.4, that is the effective length, minus the number of the end returns at the joint. So it is equal to 1441.4 mm. Now effective throat thickness we have to calculate, that is 0.7 as per the formula. Effective throat thickness 0.7 into size of the weld. So 0.7 into 8 is equal to 5.6 mm. So strength of the weld per millimeter length, there will be by this formula 1 into TT into FU by root 3 comma MW. FU is equal to 410. Okay, FU is equal to 410. FU is equal to 410. 5.6 410 root 3 1.25 for shop welding, assuming we are using shop welding. For shop welding, if you see, for shop welding the value is 1.25, and for site welding the value is 1.5. So it is taken as the shop welding. So it is 1060.47. It is the strength of the weld. Now required length of the weld will be equals to, the formula is required length will be equals to, now the applied load by strength of the weld. So applied load is equal to 1500 into 10 cube divided by the strength of the weld, that is equals to 1414.46, which is 1414.46, which is less than 1441.4, hence okay. So the design, so the welded connection that can be provided and the welded connection required, it is all meeting all the scenarios. So this is the design of the column base, that is the normal slab base. This is the design procedure. So we have discussed what is the design procedure, we have discussed what is how to design all, and we have seen an example for a normal column design. The column connection is welded connection. It may be bolted connection also, then we have to follow the bolted connection principle. So up to that, this is today's lecture. In the next lecture we will be going for the gusset base, that is the gusset plate column. We will be designing the gusset plate column and see if there are any change possible. Okay, so up to that, this is today's lecture. Okay, thank you.